This is the first lecture of Module 1 for Organic Chemistry 2 in the spring 2025 semester. So Module 1 here is on conjugation, aromaticity, and aromatic chemistry. So a couple announcements. Please, since we're not meeting during the first scheduled lecture course due to a weather delay, read the syllabus and note that we're now on a Monday-Wednesday schedule. Class is 75 minutes long. New this semester, there's no more lecture quizzes, so I got rid of those. If you're unable to attend any of the lectures, the screencasts will be posted on YouTube. You have a bonus assignment in Canvas to subscribe to the YouTube channel for a couple bonus points. And as we move along, I'll explain more about exams, but one thing I want to do mention, so it's on record, is that the final exam for this course is cumulative of both Organic 1 and Organic 2 material. So if you already have the study guide, that has both semesters of material. If you do not have it, you might want to consider buying it as you prepare for the final exam for this course. As you'll see, the grading schedule is a little bit different this semester since we don't have the daily lecture quizzes. You'll want to look at the weight distribution of how each exam affects the total outcome. Remember, you're here to, one, primarily learn, two, your grade is going to be assigned based on the number of points that you accumulate. So please read that section in the syllabus and understand how you're assessed in this course. So we'll get right into it here. Remember that we left off Organic 1 looking at electrophilic addition reactions of alkenes. And that's when you have a pi bond, which is 1 degree of unsaturation. So remember, we use that pretty extensively in Organic 1. And so a typical addition reaction, you have some electrophile, in the case shown here, that's hydrogen gas. And the elements of hydrogen are adding to each sp2 hybridized carbon of the alkene. So notice overall, we get the addition of H2, and now the carbons are both sp3 hybridized. So in this case, since that electrophile H2, both elements are the same, each carbon is getting the same thing. However, remember, if for the electrophile, if they're different, we have this issue of regiochemistry. And so that was where we had to decide which atom is getting, which atom of the alkene is getting what atom of the electrophile. And again, that was primarily determined when the reaction mechanism proceeds through a carbocation. So in this module, we're looking at this word conjugation, and then we're going to see how that relates to another term, aromaticity. So conjugation, really limited to polyunsaturated hydrocarbons. What does that term mean, and how does it affect electrophilic additions? So what are the types of polyunsaturated hydrocarbons that have, essentially what that means is poly means many, and for unsaturation, again, we're talking about double bonds. So systems with multiple carbon-carbon pi bonds, and we'll look at a couple other systems that have heteroatoms in there, just as a context of how we've seen them before. So the three scenarios that we can have are accumulated, so it's shown here in red. That is a 1-2 relationship between the pi bonds, meaning that they're both joined together. There's no separation of them. In blue, conjugated, which we'll focus on primarily, is a 1-3 relationship, meaning there's a sigma bond that separates the two pi bonds. And then in green, isolated, 1-4 or greater relationship. So there's an sp3 hybridized carbon that separates the pi bonds. So it turns out conjugated systems are special in that when the pi bonds are next to each other, there's a little bit of stabilization of the system. So here are some examples of each of those, split into two cases. So acyclic and cyclic, and the substrates shown are dienes, which means there's two double bonds. So the accumulated system is propa 1,2 diene, and so this is generally called an allene. You can see that if we number 1, 2, 3, that the start of the first alkene is at position 1, and then the start of the second alkene is at position 2. For the accumulated system, if we number 1, 2, 3, 4, you can see the start positions are at 1 and 3, and so they're separated by a sigma bond. And then the isolated system, 1, 2, 3, 4, 5, they're now separated by an sp3 hybridized carbon. And while we're at it, going back to the allene, since they're joined together, they're joined by an sp hybridized carbon atom. So at this point, if you're a little rusty on hybridization, you might want to review that in moving forward this semester. So the cyclic cases, all we're doing is tying the system, the pi bonds together in a ring. Note that there's no cumulative diene listed under here. The reason for that is they can get very strained when you do that based on the sp hybridized geometry present in that carbon atom. So we're beginning with conjugated and isolated. So same thing here. If we number 1, 2, 3, 4, you can see the start positions at 1 and 3. And so that's a 4-membered ring, as indicated by the cyclobuta part of the nomenclature. We have a 5-membered ring. So 1, 2, 3, 4, 5. And notice that they're connected now together by this sp3 hybridized carbon, but overall there's a sigma bond between them. So we have a 6-membered ring, cyclohexa 1,3 diene. Same situation here. There's the sigma bond. And if I use the highlighter, you can see there in red, there's the conjugated system. And then isolated is cyclohexa 1,4, so 1, 2, 3, 4, 5, 6, and either way they're separated by an sp3 hybridized carbon atom. So you can have, since poly means many, you can have situations where you have more than 2 alkenes. So these are trienes. So the first one is an accumulated triene butyl 1, 2, 3, 4. So butyl 1, 2, 3 triene. So that has 3 double bonds. We have a hexa 1, 2, 3, 4, 5, 6. So hexa 1, 3, 5 triene. Again, note sigma, sigma separation. And then the isolated system, we have 1, 2, 3, 4, 5, 6, 7, 8. So total 8 carbons, but 3 and 6 are sp3 hybridized carbons, so that's isolated. So moving from acyclic to cyclic, I have this highlighted in blue. 1, 2, 3, 4, 5, 6. Cyclohexa 1, 3, 5 triene. Is that a triene? Is this a triene? And as we'll see, the answer is no. This is a special molecule. It's called benzene. And because it's a conjugated triene in a ring, it has another special property called aromaticity. So one of the conditions of being aromatic is that you have to meet the criteria for being conjugated, but also in a ring, and then some other things that we'll talk about. So that'll be some of the lectures here in Module 1. But moving forward, let's look at some questions here. What is the hybridization of the common carbon atom of 2 alkenes and a cumulene? So this is the cumulene. It's cumulated double bonds. So this is the common carbon atom, and that's sp hybridized. So the answer there is A. So one thing to note about the cumulated system is pay attention to how the bonds are drawn. So on the left side, the hydrogens are in the plane. On the right, this is back, this is forward. And so the reason that is remember that for an sp hybridized carbon, you have 2 sets of pi bonds that lie in 90-degree or orthogonal planes to one another. So as you move through that carbon, you're entering the second set of pi bonds, which changes the plane in which those hydrogens exist. Which polyene has an sp3 hybridized carbon atom? So this would be C, the isolated system. That carbon atom is sp3 hybridized, so it's isolating or insulating the 2 pi bonds from one another. Which polyene has an sp2 hybridized carbon bond? So this is choice B. So you have sp2, and that's a sigma bond. So that's what that means. That's a sigma bond. And again, since that's the conjugated system, we're going to see how that arrangement of pi bonds affects the reactivity in electrophilic addition reactions. Before we move on into those reactions, we're going to just take a pause here and talk about cumulated double bonds. They're interesting functional groups. in organic chemistry, and they come up a little bit more with some of the reagents that we have learned and that we will learn. So if all the atoms are carbon of that cumulated system, they're typically called alene or alene derivatives. And then that sp hybridized carbon is sometimes drawn as just a dot, as shown here. So you can see that sp hybridized carbon, so that's a C atom represented as a dot. And as I mentioned prior, as you're moving along from carbons 1 to 2 and then 2 to 3, since they're accessing different p orbitals of the pi bonds, the plane in which those hydrogen atoms sit shifts 90 degrees. And so as you can see from the viewpoint, if you're looking at a Newman projection, that through that carbon atom at 1, those carbon atoms on carbon 1 would lie horizontal. And then going through the sp hybridized carbon to carbon 3, you see the back ones are lying now vertical. And so that is a 90-degree rotation as you move through carbon atom 2. And what is interesting about that property is now if you have different substituents on carbons 1 and 3, the alene will be chiral and it can have enantiomers. What is sort of different about how you assign R and S is, or what is the same, you're still looking at the attached groups to those carbons, but when you determine the clockwise or counterclockwise, you're now only considering substituents 1, 2, and 3 in your rotation. So if we look at the case shown, so here's our viewpoint, and now we're going to look at this carbon right here, and so those are going to be in the plane, so they're horizontal. And we assign priority to them. The carbon atom gets priority 1, the hydrogen gets priority 2. Now if we look at the back, or carbon 3, put that as a square, you do the same thing, but now you're going to continue the priority. So the carbon of the ethyl group gets 3 and the hydrogen gets 4. And so when you're determining whether to go clockwise or counterclockwise, you're always staying on the front carbon atom. So we're going to go 1 to 2 and then to 3. And that's really all we're considering is the rotation of that steering wheel. Since this is going counterclockwise, it ends up being S. And since the mirror image is the enantiomer, we see 1 to 2 to 3, and so this is going to be R because it's clockwise. So at this point, we would pause for any questions. I do encourage you during the lecture to throw up your hand and ask questions. This is the dedicated time for that. If we're on a specific slide and you want me to pause as well, please throw up your hand and ask the question. so that we do not move forward with any misconceptions about the concepts we're discussing. So as I mentioned, you can also have these cumulines with heteroatoms, so these are called heterocumulines. And again, the central atom is going to be sp hybridized. So sp, sp, and now we've substituted the terminal atoms off for either one or two heteroatoms. In the first case, we see both of those atoms at positions 1 and 3 have been substituted for oxygen, so this is carbon dioxide. And the number in red here is equal to the oxidation state, where we're counting the number of bonds from the carbon to the heteroatom. So we've seen carbon dioxide in Organic 1. A new reagent that we'll learn this semester is called NN dicyclohexyl carbodiimide. And this reagent is used for peptide coupling. So basically making amides. And as we'll see later in the semester, these are called peptides. So you see the two heteroatoms at positions 1 and 3 are both nitrogen. This also has an oxidation state of 4. So what's unique about these oxidation state 4 reagents, we know that in the oxidation state ladder, carbon being at 4 is the highest. So from 4, it can only undergo addition reactions, which overall means a net reduction. So in the case shown here, we're taking bromobenzene, and what we're going to do is treat that with magnesium metal in step 1 here. And what that's going to do is insert magnesium into the carbon-bromine bond. And this is essentially making a carbanion. So you might want to review the reactive intermediate types of carbon as we move forward. So if this is a carbanion, it's supplying a negatively charged carbon. We're going to react that with carbon dioxide. That carbon is delta positive, so it will be attacked by the carbanion, and that's going to form now this carboxylate, which is negative. And so overall, if this started oxidation state 4, it goes to 3, and then we do an acid-base reaction with aqueous HCl to protonate it, and we end up with the acid, which is now oxidation state 3. As part of this module, again, we'll learn how we take benzene and we make substituted derivatives of benzene, and this is another new mechanism we'll learn called electrophilic aromatic substitution. The important thing to note is that the S, it's a substitution of an existing hydrogen for some other group. So even though benzene has the 3 pi bonds in it, the carbon atoms of the pi bond do not both undergo addition. Only one of those undergoes an addition, but then based on the mechanism, it's a substitution of hydrogen for something else. So a couple examples before we get into some specific reactions here. The molecule shown here is called calcitriol, and you can see 1, 2, 3 alcohols. That's where the triol part comes from, and is the active form of vitamin D, a hormone that increases calcium 2+ ions in blood. So it's made in the kidney, and the question asks, what type of polyunsaturation does this molecule have? So if we visually look down for the sp2 hybridized carbon atoms that are present in the pi bonds, we see 1, 2, 3. They're separated by sigma bonds. So overall, this would be a conjugated system. So this molecule shown is 7-dehydrocholesterol, or provitamin D3, and it's the precursor to calcitriol. So what type of polyunsaturation does it have? Same thing, we identify the pi bonds. We see that they are separated by a sigma bond, so this is also conjugated. Provitamin D3 is converted to calcitriol by the action of sunlight, and then liver and kidney enzymes consider the conjugated diene becoming a conjugated triene. And what I've shown here with the blue ball, so this is a methyl group, CH3. That becomes CH. And the hybridization also changes from sp3 to sp2. So basically what's happening is you're getting a cleavage about that bond, and then you're getting a hydrogen migration to form calcitriol. How many sp2 hybridized carbon atoms are converted in provitamin D3 to calcitriol by photoconversion with sunlight? So all we're doing here is counting. So if we start here, so 1, 2, 3, 4. So there's 4 on this side. We count here, 1, 2, 3, 4, 5, 6. There's 6 on this side. So 4 to 6, the answer is D. So this is probably a little bit more complex example of dealing with conjugation, but what's interesting about it is, again, the conjugated pi system is what makes this happen. So again, to reiterate, we would pause for questions at this point. So now we'll get into some of the physical organic chemistry and understanding why conjugated systems behave a little bit differently than just isolated pi bonds. And as a backdrop to that, we're going to use the heat of hydrogenation experiment. And again, that was what we first introduced in this lecture, where we're adding hydrogen gas to an alkene, so the electrophilic addition of H2 to a pi bond. And shown in the table here are 5 different compounds, and they're classified according to their substitution pattern of the alkene. So we have a monosubstituted alkene, a second monosubstituted alkene just with another carbon, a disubstituted alkene, an isolated diene, and then a conjugated diene. And so if you look down the H2 column, that's the equivalence of hydrogen gas that we have to add to fully hydrogenate the molecule. So you can see at this point there's a difference 1 to 2 because we're now having 2 alkenes in the molecule. The fourth column is the enthalpy change in kilojoules per mole. The fifth column is the enthalpy change divided by the moles of H2 that were used. So essentially you're either dividing that by 1 or 2 based on column number 3. And then the last column is just some comments about the trend. So row 1, your average monosubstituted alkene will give off negative 127 kilojoules per mole when it's hydrogenated. You can see that row 2 confirms that you have a similar substrate but just a longer carbon chain. Now row 3 is a little bit different. We're going to a disubstituted alkene. And you can see it's giving off less heat, which means that it originally is more stable than a monosubstituted substrate. Now, if you look at the fourth entry with the isolated alkenes, total they give off negative 254. We divide that by 2, you get negative 127. So this number is about equal or is equal to those alkenes being just 2 separate pi bonds in the molecule. And again, it's isolated because of that sp3 hybridized carbon. Now the difference, the important part, the 2 alkenes are now separated by a sigma bond. Notice that when we hydrogenate that, the difference is much lower, negative 239. So we take that, divide by 2, we can now get negative 119.5. And so the difference between these two numbers here is telling us that when the double bonds are conjugated, there is an extra stabilization inherent in the molecule because they're giving off less heat when they're hydrogenated. And so we want to understand why that is and how it affects other electrophilic addition reactions. So as we mentioned, we have this isolated case here versus the conjugated case. You can see that in the isolated case, these again, because they're isolated, they behave as just regular alkenes. But now when they're conjugated, there's less heat evolved. And so that indicates stabilization. And again, the word we use for that now is just called conjugation. It's important to realize, again, that we're building up on these concepts throughout the semester, so conjugation is also going to help us understand the other term, aromaticity. You can see that in the lengths of the bonds through the conjugated system, that between carbons 2 and 3, you have, again, the slightly longer bond length because that is a sigma bond. So to get down on the molecular orbital level of understanding why this is important and how it affects not only chemical reactivity but physical properties, we want to examine the p orbitals that are involved in forming these pi bonds. On the left, we see just one pi bond. So I have these four substituents. They can be anything coming off it. On the right, now we have two pi bonds connected together by a sigma bond. So in that case, they're conjugated. So on the left-hand side, we know that a pi bond is made up of two p orbitals. And if we start from the bottom of this energy diagram, we see that this psi1 here, to make up that pi bond, the phases of those orbitals have to be aligned so that you get sharing to form the pi cloud. So we're starting with two p orbitals. And since that is a bonding molecular orbital, we have to have a second anti-bonding, so psi2, and that's what that little star means, anti-bonding. Since that's a different orbital, now the phases are not aligned, and that's indicated by the color of the lobes. And so since they're not aligned, where that color or phase change happens, that's called a node. So overall, for n atomic orbitals, there are n molecular orbitals involved. And the number of nodes per molecular orbital is always your whatever molecular orbital you're looking at minus 1. And so let's demonstrate that by looking at this diene system here. We see that there's two pi bonds. So that equals 4 p orbitals. So meaning we have 4 wave functions to describe that. The lowest energy wave function is always going to have 0 nodes. And again, if we take 1 minus 1, that gets 0. And we see that because the colors or the signs or the phases are all aligned. So you have this pi bond, then this one, and then this one. And there's no change between any of the p orbitals. So as we go up in energy, we're now at psi2. We have another bonding molecular orbital. So 2 minus 1 equals 1. So this should have 1 node. And we see that it exists between carbon atoms 2 and 3. That's where that phase change occurs. And since we're dealing with even numbers, so 4 p orbitals, 4 molecular orbitals, we're always going to take the total, divide by 2. In this case, that means there's 2 bonding plus 2 anti-bonding to get us the 4 total molecular orbitals. So at this point, notice the little change with this asterisk. Those are the anti-bonding orbitals. Essentially what that means is the bonding orbitals always have electrons in them. The anti-bonding orbitals do not because they're higher in energy. We will see situations where they come into play, specifically related to when we see the color of a substance. So looking at CHE3, which is an anti-bonding orbital, so this now has 2 nodes. You can see the node between 1 and 2 and between 3 and 4. CHE4 should have 3 nodes, so essentially we're going to alternate as we move along the carbon chain. So what wave function of the 1,3 diene system has 2 nodes? And again, we're using this wave function number minus 1. So if we wanted to find the one with 2 nodes, 3 minus 1 would equal 2. So it's going to be answer C. And so we can see here is a node and there is a node. And to reiterate, a node is just a region where there's no electron density between those orbitals. So at this point, we would pause for questions. Remember, as I said in the beginning, the lectures are 75 minutes now, twice a week. We no longer meet on Fridays. So let's put all this into practice now by looking at an addition reaction involving a conjugated system. So as we drill down into this, we're going to revisit these terms: thermodynamics versus kinetics. So thermodynamics typically relates to stability, and kinetics rate. We're going to start with butyl 1,3-diene, and again pi bond, sigma bond. The electrophile we're using is HBr. In these reactions, the alkene is always acting as the nucleophile, and the electrophile, the other thing, is accepting the electrons from the nucleophile. So as highlighted in the 2 possible products, we see that one of them is 3-bromo-but-1-ene. There you can see the addition of HBr across carbons 1 and 2. The second is 1-bromo-but-2-ene. Now those atoms of the electrophile have been added to the 1 and 4 positions. So there's 2 possible products that can come out of this. 1-2 addition, they're right next to each other, or 1-4. And if you look at the temperature, we have 2 entries, 0 degrees and 40 degrees. At 0 degrees, the 1-2 addition product is favored. At 40 degrees, the 1-4 addition product is favored. And so overall, the form of this reaction is your starting material A is going to 2 constitutional isomers, B and C. So everything being the same, really what is controlling it is the temperature variable. So 0 degrees is your standard ice water bath. 40 degrees is about 15 degrees higher than room temperature. Again, We're in degrees Celsius here. So how can we start to explain how temperature affects the product distribution? So what we'll do is we'll draw out the mechanism, and then the remainder of the slides will just be some questions that individually probe the concepts. So there's the 1-2 addition. And here is the 1-4 addition. So we put our lone pairs in on bromine. We can say that's delta minus, hydrogen's delta plus. The first step in this, we do have to make a choice. So let me number 1, 2, 3, 4. The pi bond is going to abstract a hydrogen atom. So if we're just focused on carbons 1 and 2, alternatively you could use 3 and 4. The arguments will be the same. Which carbon atom 1 or 2 is going to abstract that hydrogen? So let me slightly redraw this. We can show which one's preferred and why. So down here I'm going to draw 1, and here I'm going to draw 2, which indicates the carbon that gets the hydrogen. So from the pi bond, we're going to use that to abstract the hydrogen. If we go down path 1, carbon 2 is going to end up as a carbocation. If we go up path 2, carbon 1 is going to end up as the carbocation. And at this point, we would classify them. This one is secondary, and it's allylic. This one is primary. And so we can recall from the carbocation stability trend, tertiary is greater than secondary or is greater than primary. And then allylic and benzylic have special stabilization. We know from this case that secondary is going to win. And as I've drawn it, it is lower in energy. So if we were considering energies, the secondary is lower in energy, so that path is preferentially followed. So we're immediately going down this path. We're not following that path. And so now we have this secondary allylic, and if we were at colder temperatures, so 0 degrees, we still have this now bromide anion in solution, and it would immediately trap that carbocation. And so we would end up with the secondary allylic bromide. as the major. Notice that we still get some of the minor to a lesser extent. But how do we form the 1,4 when we elevate the temperature? So this is the important part here, allylic. There's a resonance form where we shift those electrons of the pi bond to now an internal alkene, and we end up with a primary and allylic carbocation. So the same thing, we still have the bromide anion floating around that will trap that, and this will go to the major as 1,4 to give primary allylic bromide. And so we'll say major T equals 0, major T equals 40. And so this gets down to why we're explaining how the temperature affects it. In the 1,2 edition, that's a kinetic. So at colder temperatures, that secondary allylic carbocation is trapped faster. In 1,4, we're at 40 degrees. That's thermodynamic because if we look at this pi bond, this is di-substituted and trans. So when we're talking about stability, we're talking about the stability of the alkene. And we had learned that tetra-substituted is greater than tri, is greater than di, is greater than mono. So at colder temperatures, the trapping of the secondary carbocation is faster. At higher temperatures, we're dealing with the primary allylic carbocation, but when that's finally trapped, we're ending up with a more stable product. So to review everything we just talked about with a couple questions here, which of the following correctly describes the products? So this was the 1,2, and this was the 1,4. The 1,2 is going to be kinetic. The 1,4 is thermodynamic. So the kinetic product is going to be the 3-bromo-1-butene, and the thermodynamic is going to be the E1-bromo-2-butene. And remember what these nomenclature descriptors mean. That's describing the geometrical isomer of the alkene. So E is trans, Z is cis. How many unique sets of proton does each product contain? So this is, again, an important concept in why we studied it in semester 1. The reaction is producing 2 constitutional isomers, and then we would differentiate them according to spectroscopic methods. So 3-bromo-1-butene. This is a CH3 group here, even though I've just shown one of the H's. So there's one set. Here's CH. That's 2. Now we need to draw this H. That's also unique. And then these 2 H's here, even though they're bonded to the same carbon, they're not the same because they have different relationships to each other. So overall, we would end up with 5. So 1, 2, 3, 4, and 5. And again, keep in mind, we learned about angular dependence of coupling. And that's the reason why those are different. For the second one, we have a CH3 group 1, this H, and then this CH2 group, so that's going to be 4. 1, 2, 3, 4. So our answer here is going to be A. By what reactive intermediate does this addition reaction proceed? This will be a carbocation. We see there's protonation. So these are the main reactive intermediates we studied in Organic 1. Carbanion, carbene, carbocation, radical. So you'll want to review the context of the reactions and mechanisms in which we saw those intermediates. So as we saw in the mechanism, we're going to protonate carbon 1 because that's leading to the most stable carbocation, which we said was secondary and allylic. So you'll want to review this stability trend as we move through the semester to understand how we can arrive at predicting what is major versus minor. So that was the carbocation. We determined it was secondary based on the number of carbon substituents bonded to it. And it was allylic because it has this pi bond bonded to it as well. So secondary allylic. So what is crucial in this mechanism is the resonance form due to the secondary carbocation being allylic. And again, resonance is just the movement of electrons. You're not moving atoms. So in this case, the pi bond electrons move over, and then that plus charge migrates from position 1 to 3 using relative numbering. So I want to point that out, that the numbering is relative. Resonance is always going to involve a 3-atom system. In you're moving either electrons or you're moving, electrons as lone pairs or electrons in pi bonds. And then you're, in this case, we're conserving that plus charge from the secondary to the primary position. So at lower temperatures, the 1,2 addition product dominates. That's the kinetic addition of the bromide to the secondary allylic. That's the more stable carbocation. These resonance forms are not there in equal percentages per se, but to inform you that in the charge distribution, one is more favored than the other. In increased temperature, the less stable primary allylic carbocation intermediate is trapped by the bromide, leading to the 1,4 addition product. That's the thermodynamic product because the alkene is more substituted. So again, as you go through these problems, try to always, write down or say out loud the justification for why you're choosing one thing over the other. So to visualize the reaction, as we said, A going to B plus C, we have the reaction coordinate. And again, the x-axis is a time element, and the y-axis is energy. So here are our starting materials. On this side are the products, B and C. And then we have these situations in between. We talked about transition states and intermediates. Overall, this is a pretty generic reaction coordinate in that it does not fully describe all the intricacies present along the reaction pathway, but rather just A and then the final resting states B and C. So which point corresponds to the kinetic product? And so we said kinetic was dealing with rate. And so what affects the rate is the energy of activation. So starting from the starting materials, point A, I'm just going to draw this line across at that energy. And then we see the two curves going to either B or C. And then at each point, we draw the line up. And that would correspond to the energy of activation. We can see that going along the red path towards B is a lower hill to climb, so that's going to correspond to the kinetic product. Again, it's easier to get over hump B than it is to C in terms of the rate. Which point corresponds to the thermodynamic product? Using our same line. Now we're going to draw the line down, and we can see that we drop down further to point C, which indicates C is more stable than B. That's what we mean by the thermodynamic product. So to summarize that, again, this is an abbreviated reaction coordinate. It's not showing all of the transition states and all of the intermediates. We can see that along the two pathways, we have the energies of activation, these lines going up, and then the total free energy of the reaction, these lines going down. So here we're concerned with rate, and down here we're concerned with stability. So let's look at a couple reactions where the substrate is slightly different, but to keep in mind for this and moving forward throughout the semester, I'm highlighting the conjugated system in red. And so we started off with this system. And now all we've done is we've embedded that system into a ring. So it says protonation of the diene with HBr will generate an intermediate best described as. And as we saw before, we want to protonate a terminal carbon atom, so that deposits the carbocation in an allylic position. So if we do that, we're going to protonate position 1. That's going to generate carbocation at position 2. and then the remaining alkene at 3 and 4. So if we classify that, it's secondary and allylic, so the answer is D. So now again, if we were to protonate position 2, so just to show you what is not preferred, we're generating that carbocation. So it's secondary, but not allylic. So that's not preferred because you're not stabilizing the plus charge any. How many total alkyl bromides will cyclohexyl-1,3-diene produce when subjected to HBr addition? We know that we're moving through this secondary allylic carbocation intermediate. So if we trap that in the 1,2 sense, we'll end up with this product. If we look at the resonance form of this, and then we trap that, we can see that based on the starting material having no other substituents on the pi bonds, we do end up with the same thing. So that's an identical molecule. However, we've now generated a stereocenter. So we get R plus S enantiomers. So we're going to end up with 2 total alkyl bromides. So another similar situation, I'll highlight the conjugated system in red. We've just moved the substituents around a little bit. What is the classification of the alkyl bromide produced as the kinetic product? So if we protonate position 1, that generates a secondary allylic carbocation. We know that if that's trapped in the 1,2 fashion, we're now ending up with this product, and that would be a tertiary alkyl bromide. So tertiary, it's also allylic alkyl bromide, so C is the correct response. So the thermodynamic product, again here, this is going to rely on invoking that resonance form. Where now the double bond is shifted internally. So now we have a tetrasubstituted alkene. We're trapping with bromine. And so our product here is going to be primary allylic. So thermodynamic, this is the 1,4 addition. And so that's going to bring us to the end of lecture 1 of module 1, looking at electrophilic additions. Where we're going with this, we're going to look at another type of addition reaction, but it's called a cycloaddition. We're going to look at the impact of molecular orbitals on the color of organic molecules. So color meaning like dyes in clothing or dyes in food as food additives. We'll talk a little bit about the economic impacts of advertising and how color is used to get you to buy something. We'll understand how conjugation impacts color, what makes color pleasing, and eventually we'll get into that second concept of aromaticity, where we deal with aromatic compounds and their reactions.